Previously, we discussed the intuition behind the Heapify process, and then we also looked at the heapq module in Python, which has a neat function called Heapify that creates a list, that takes in a list as an argument and converts that list in place into a min heap. This video will talk about the complexity of the Heapify operation, because obviously we are always interested in how does the complexity of an algorithm look like, how does it scale as, for example, the size of the input becomes large. It turns out that Heapify is in fact an order of n algorithm. This is very, very interesting result. Notice we are doing lots of swaps, but this is in fact order of n, which means that if my list size were to become 10 times as large, I expect the running time to also increase, let's say approximately 10 times. Now, the proof for this is a little bit mathematical, so I'm not going to get into that. Of course, I'm happy to discuss with you if you're interested, but let's anyway look at the intuition, because we have seen how Heapify works at an intuitive level. In fact, that's sufficient to convince us that this is in fact quite logical. Think about it. We know that leaf nodes are always heaps, because when it comes to leaf nodes, there are no children, nothing to compare, hence all of them are heaps. And let's say if you have a perfect tree or close to perfect tree, in fact, almost 50% of nodes are are leaf nodes, which means that for 50% of nodes, really nothing to be done. We can see this as an example. For example, let's say I had this list to heapify, perfect tree here. Basically, out of 7 nodes, 7 items, for 4 I had nothing to do, because there cannot be a heap violation in these at all. Now, when I go one level up, the number of nodes that I have is half of what I had in the lowest level, in the leaf level. That's 2. And I'm going to do at most one swap to fix the, let's say, the heap violation over here. So in this case, the swap that was made, for example, is 49 going to 53. So 49 swapping to 23, I'm sorry. 49 to 23 swapping becomes a heap here at this node. So for this node, at most one swap. For this node, definitely there could be 2 swaps as have been done here. So 77 has gone from, let's say, being on top on the root to the leaf level, but 2 swaps done here. So the point is, look, as we go higher and higher up, most of the nodes we find nothing to be done. Half of those nodes we find, okay, maybe 1 swap. Another half of from there, maybe 2 swaps. Another, let's say, half from there, maybe 3 swaps, and so on and so forth. When you aggregate all of this, you'll realize that the complexity goes to order of n. Like I said, the maths behind it is a little bit complicated, but if you are interested, definitely happy to think about it. What we will do instead is to put this in perspective by comparing this to sorting and, let's say, min find. We'll do that in the next video, but I hope you found this interesting. Do think about it. Like I said, having an intuition into how Heapify works helps us understand why the complexity is in fact order of n. And this is actually a very, very, very powerful result. We'll see the implications a little bit later. At YByte, we always learn algorithms and programming in a fun way, focusing on the key concepts without getting lost in jargon. Do look at our website, www.ybyte.in, and enjoy programming. Take care. Thank you so much. Bye-bye.